Welcome to Fundamentals of Telecom 2. In this video course, we're going to drill into the technology of the PSTN just a little bit to understand digital transmission. We'll start off looking at how voice is digitized, the standard way of doing that on the PSTN called a DS0, how those are combined into higher speed streams, DS1s and DS3s. We'll take a look at the applications for digital besides voice. We can talk about data, of course, and we're going to talk about digital video a little bit. And then in the second part, we're going to take a look at digital transmission on the PSTN and understand the idea of channelized multiplexing. We'll take a survey of different technologies like T1, T3, SONET, and dense wave division multiplexing. Now, before anybody says this is all old stuff and we don't need to know it, the vast majority of the installed base runs on SONET fiber optic transmission systems and channels. Yes, we will be going to an all-IP packetized network sometime around 2025. The changeover should be complete. But a lot of the time these days, we're talking still about circuit-switched DS0 communications for voice, and we're talking about channelized SONET fiber optic transmission systems. So this is still part of the fundamental knowledge you have to understand the telephone system. Before we jump in and talk about what digital is, I'd like to discuss why we'd want to do that a little bit. And there are 6 main reasons for using digital techniques. These are circuit density, error performance, integration, and processing. Now, why are the first 3 reasons circuit density, and what exactly do we mean by that? The idea is that some company like AT&T is going to buy a fiber optic based transmission system from some company like Alcatel or Nortel that's capable of moving an enormous number of bits per second from A to B. Then they're going to buy multiplexers of one kind or another, and there are a couple of ways of doing multiplexing. And what we'll do is put one multiplexer at each end of this high-speed transmission system. And what the multiplexer does is takes in a whole bunch of lower speed inputs, combines the information on those inputs together into a high-speed stream to be carried over the high-speed transmission system. And then the multiplexer at the other end breaks it back out to the original lower speed streams. And the whole idea in this is that the number of circuits that's being carried on the transmission system in the middle is not 1, it's the total of all the lower speed circuits. Some of the crustiest, oldest stuff that we still use is called T1. The number is 24. You can move 24 individual circuits on a single high-speed transmission system with T1. Off-the-shelf stuff like OC48, the number is 32,256. Those are the first 3 reasons for using digital. It's very easy to combine stuff together using digital techniques. I mean, you can do multiplexing using analog techniques, like cable television is analog, but it's pretty noisy and it's not very efficient. As we're going to see in this course, all we end up doing is interspersing bytes to do multiplexing. Another main reason for using digital transmission is that it's a better way of representing information from a noise point of view than is analog. The idea with digital is that we code our thoughts into 1s and 0s somehow, and then we do something like apply a voltage to the line for a certain amount of time and then not to represent a 1. Or we could turn the laser on for a certain period of time and then turn it off to represent a 1. So what we're doing is we're applying a second state to the line and then not for a certain duration of the time. And you could represent this as a little square pulse on a diagram if you wanted to. Now the beauty of this technique is that you can tell the difference between a square pulse and fuzzy noise that gets added to it during transmission. So when we get to some intermediate point in the transmission system and we have to do something with the signal, we can throw the noise away and just send a nice clean copy of the signal down the next cable. As compared to analog, as we're going to see later on in the course, we actually boost the noise up and send it to the next people down the line. So with digital, by coding our information into ones and zeros and then representing that using pulses, we can transmit information from here to Hong Kong without adding in any noise. So quiet you could hear a pin drop. Another reason for digital is integration. Does it make any difference whether the first input in this system is a digitized form of somebody speaking and the second one is an email message being transferred from one mail server to another? Well, not really. You'd want to know what the delay was going from one end to another and what the variability in that delay was, because variable delay is very important to the quality of the reconstructed sound. But other than the question of transmission delay, no, it doesn't make any difference. They're just ones and zeros. The transmission system doesn't know what these ones and zeros are supposed to be meaning. Now, if you take this idea that we can integrate all of the different services you've ever heard of before onto a single high-speed transmission system, and you add it to the first idea that we can do lots of that, what do you get? Money. Lots and lots and lots of money. This is the telecommunications business. We take one high-speed circuit and we carry all of the services over it. And of course, what the phone company is doing is they're buying wholesale and charging retail. This is the telephone business. One last reason for using digital techniques is processing. Once we have, for example, a voice coded into ones and zeros, then we can process those ones and zeros with a microprocessor. An easy example of that would be a computer system that has special hardware cards on it and a big hard drive. And we could attach this to a telephone system, and what it would do would be receive digitized speech over the network and compress that speech. In other words, use fewer ones and zeros to represent it and store it in files on a hard drive. And then when somebody wanted to listen to it, they could access that system and it would grab the file off the hard drive and play it back over the network to them. What's this? Well, a voicemail system. That's what voicemail is. It's a computer with hard drives on it and usually special hardware cards for doing real-time compression. If you call somebody and they don't answer, it rings 3 times, it does a no-answer transfer to the voicemail computer, which then plays a message over the network to you and then listens and records what you've said and stores your message in a file on a hard drive. And then the user subsequently can pick up their phone and press *89 or whatever it is to access the voicemail system and then use their touch tones to tell the voicemail system which file to get off the hard drive and play back to them. Anybody's ever fooled around with MP3 or WAV files on a computer, well, that's all this is. Probably more sophisticated and faster, but that's all a voicemail system is. Another example of processing would be speech recognition, and a third example would be speaker recognition. Speech recognition has become pretty good over the last while. We can now do fairly sophisticated connected speech recognition, where we can write a computer program that would understand what I'm saying right now, even if I spoke like this. Well, maybe not quite that good. 10 years ago, you would have had to speak like this with single words for it to understand what you were saying. But now we've got to the point of connected speech recognition. And I know, for example, my telephone company, if you phone for customer service, you want to add call forwarding to your line, you talk to a computer and you can talk in natural speech and it actually understands what you're saying. That is speaker independent word recognition, and it's a number of words put together called connected speech. Another story is the idea of speaker recognition, and we might start to see this used for fraud prevention. The idea here is that when you first get your credit card or your calling card from the phone company, when you're activating it, you would have to record some standard phrase. And the standard phrase we like to use is your own name, because you always pronounce that the same way. So when you activate it, you would say Eric. Now the idea is that when you were doing an online purchase, it would say your name, and you'd say Eric, and it would go off in a database to check to see if you said that known phrase the same way this time as you did when you activated it. And the idea here is that if somebody has stolen your credit card number, but they have not met you, they do not know how you speak. And so even if they say the same word, Eric, a computer program is going to be able to tell the difference between them saying your name and you saying your name. And so we can use this for authentication. The assumption is that they have never met you, though, because a mimic can defeat this system. I hope that you've watched Fundamentals of Telecommunications Part 1, so you have a fairly good idea of what we mean by the term analog. Analog means representation. So an analog signal is like, for example, a voltage that we put on the wires, which is a representation of the sound pressure waves coming out of the speaker's throat. People stretch the terminology to refer to the two wires that are carrying this analog as an analog circuit, but that's not very precise because we could use those same wires to do other things like digital communications. The capacity of a circuit is called its bandwidth. Bandwidth means capacity. And in the analog world, capacity is measured literally by the width of the frequency band you have to play with. And that's measured in hertz. Now, a digital signal is not where we put one wave of, say, electricity on some wires as a direct representation of the sound pressure waves coming out of your face. No, the idea with a digital signal is that somehow we take the information and represent it using ones and zeros. And a digital signal is a sequence of ones and zeros that's transmitted from one place to another. A digital circuit, then, is a circuit that was specifically designed right from the beginning to move ones and zeros from point A to point B. Bandwidth is still used to mean capacity, even though we're talking about digital circuits. However, in the digital world, bandwidth is measured in bits per second. So bandwidth means capacity. In the analog world, it's measured by the width of the frequency band you have to play with. In the digital world, it's measured by how many bits per second you can move from A to B. You don't really want to start talking about hertz on a digital circuit, or you're going to get things mixed up real quickly. What I'd like to talk about to understand the idea here is the idea of representing information using ones and zeros. And in particular, I'd like to understand how we represent speech using ones and zeros, because this is the basis for the vast bulk of the public switch telephone network is moving digitized speech around. To explain the idea of how we digitize speech, I'd like to introduce two words into the discussion: continuous and discrete. These are the two kinds of signals in this world. Continuous signals are ones that are defined everywhere. Length, width, height, time, all of these things are continuous. My arm is continuous. Within obvious limits, my arm is defined everywhere. There are no holes in my arm. Now, what does this have to do with analog and digital? Well, most analog signals are continuous. I can think of some examples that aren't, but let's not. What's an example of a continuous analog signal? Well, how about those thermometers that you can buy at Home Depot, and they come with metal brackets so you can mount them on the exterior of your bedroom window facing in, and if the sun isn't shining on it, it gives you an idea of what the outside air temperature is. What's this? It's a tube of glass with some mercury in it, and as the outside air temperature goes up, the height of mercury in the tube goes up. As the air temperature goes down, the height of mercury in the tube goes down. So the height of mercury in the tube is an analog of the outside air temperature. This is all we mean by the term analog. And it's a continuous analog. The height of mercury in the tube can take on any fractional value it wants. Now, what's a discrete signal? A discrete signal is one that's not continuous. It's not defined everywhere. It's only defined in specific places, and it's not defined in between those places. Finding an example of a discrete signal in the world is kind of hard because the world is continuous. But I finally thought of one. How about the number of people in a room? You can have either 20 people in a room or 21 people in a room. But there's no such thing as 20 and a half people in a room. If you took a person and chopped them in half, by definition, those two pieces no longer make up a person. The Supreme Court would not afford either piece constitutional protections. No, the number of people in a room is discretely valued, and it can take on values like 18, 19, 20, 21, or 22, but it's not defined anywhere in between. What does this have to do with analog and digital? All digital signals are discrete. This is the whole idea. And usually when we're talking about analog digital conversion, we're talking about converting from a continuous representation of something to a discrete representation. And what the idea is that we want to take a sample of the value of the continuous signal at a specific point of time and give that value a number and transmit the number from here to Hong Kong. To make that a little bit more clear, let's go through an example of converting from analog to digital and back again. And we're going to use voice as an example, and there's a real good reason for doing this because the bulk of the public switch telephone network is all designed to carry digitized voice around. Just to put this into context, where this is going is on the line card on the telephone switch. We use analog techniques on the last 1.5 miles of wires, but the first thing that happens to the information when it gets the line card on the switch is it's digitized. And it moves through the switch as a sequence of ones and zeros. All of the transmission is digital, so it goes to the far end switch as a sequence of ones and zeros, moves through the far end switch as ones and zeros. But if you call me, I don't have a digital access line. I don't have ISDN. I've got POTS, plain ordinary telephone service. I've got an analog access line. So on my line card, that sequence of ones and zeros has to be used to recreate the analog waveform to deliver it the last 2 miles down the wires to my home. So we do analog digital at the near end line card and then digital analog at the far end line card. To do the analog digital conversion, there are 3 steps: quantization, sampling, and coding. What is quantization? Well, look at this wave here. This could be, for example, the voltage on the wires while you're talking on the phone. And you can see that it's continuous in value. It can take on any fractional value it likes, and it's continuous in time. There's always a value on the wires. We're not turning it on and off. The first step is changing this from being continuous in value to being discrete in value. And what we do is we take the range of values that the signal could possibly take on and divide it up into a number of steps or levels or bins, they're called sometimes. And then if we want to know what the value of the signal is at a particular instant in time, well, we don't look and say, well, it looks like at that time it has minus 0.73 volts. No. It's in bin number 3. It's level 3. Nice whole even numbers. No more fractions. This is called quantization. What's another example of quantization? Sugar cubes. If you have a bowl full of loose sugar, you could take any fractional value of a teaspoon you wanted. And it would be very difficult to tell somebody else how much sugar you have because that's just some random fraction. However, if we take that same sugar and quantize it into sugar cubes, your choices are now 0, 1, or 2 lumps. And it's very easy to tell somebody else how much sugar you've got because you just have to tell them what increment number you're at. The second step on this chart is sampling. Quantization changes the signal from being continuous in value to being discrete in value. Sampling is the same thing but in time. And the way that this works is like a clock. On a regular timed basis, we look at the signal and take a sample of its value. So at the first sampling time, we look and we see that the signal is sitting right here, which is within level 5, so we write down a 5. And then a little while later, it's within level 2, so we write down a 2. Then a 1, then a 4, then another 4, then a 2, then a 4, a 5, a 2, a 3, a 6, a 3, and a 1. And we end up with this sequence of numbers representing where the signal was at each of these times. This is our digital signal. And you can see that it's discrete in value and in time. Sorry to break the bad news to you, but you know all of these circuits that everybody calls digital circuits? They're not. Never heard of a 5 before. If you sent them a 4, they would have no idea to what you were referring. They've only ever heard of 1s and 0s. They're all binary transmission systems. So the last step is the coding step. We have to somehow take the raw output of this quantization and sampling and code the values of the samples into 1s and 0s. Anybody who knows binary math would know that you could represent a 5 as a 101 and a 2 as a 010 and a 1 as 001. That's the easiest way to do it. That's straight decimal to binary conversion. There are lots of other ways of doing that coding step. But in any case, what we end up with is this stream of 1s and 0s. This is what gets transmitted through the telephone switch. This is what gets transmitted over the fiber to Hong Kong. And this what gets transmitted through the telephone switch at the far end. Now, as I said, if you call me, I don't have a digital access line. I've got an analog one. So we have to do a conversion back to an analog representation. So let's take a look at that. So here we're talking about reconstructing the analog signal on the far end line card to be able to represent the information on an analog circuit the last 1.5 miles down the road. And what we have is this stream of 1s and 0s coming in. Let's just say for the moment that we don't get confused and think that these 3 bits go together as a group, or these 3 bits go together as a group. But no, we know that these 3 bits go together. So we see a 101 and we decode that and we say, aha, well that means level 5. So we put the voltage, which corresponds to level 5, on the loop at the far end. And then a while later, a 2 comes along, so we put the voltage that corresponds to level 2 on the line, and then a 1, and then a 4, and a 4, and a 2, and a 4, and a 5, and a 2, and a 3, and a 6, and a 3, and a 1. This is doing the decoding step at the far end, and then to complete the digital to analog conversion, we connect the dots in a nice smooth fashion that never varies more often than 3,300 times a second. And what we've ended up doing is recreating the analog signal at the far end exactly the same as the one that we started with. Exactly the same? No, not quite. Here's where the signal originally was at this instant in time, and here's where we reconstructed it to be at the far end. And what's the difference between these two? Well, the idea here is that when we transmitted a 5 down the line to the other end, we didn't say where within level 5 it was. This is the whole idea. We're not sending fractions anymore. And with no other information, they always have to put it right in the middle of the level. And the difference between the middle of the level and where it actually was is a little error that happens. It's called the quantization error. It's a little bit of noise that gets added into the signal when it's reconstructed, and once it's in there, you can't take it out again. This is why certain individuals would claim that compact discs represent information less faithfully than those phonographs, because CDs are digital, so they have quantization noise in them. Phonographs are analog, so they don't. Phonographs have all sorts of other horrible distortions in them, but those people ignore those and concentrate on this one. Now, how could we reduce the value of this quantization error on average? You have to be careful here. In class, sometimes people say sample more often. And that's the wrong answer, because this is not an error in time, it's an error in value, and the quantization and sampling are separable processes. So what we're talking about is an error in this direction. So the way that we could reduce that quantization error on average to a smaller value is to make the levels finer, or more levels within the same range. How many levels do we use on the telephone system? 256. Now you might ask, well, why do we use 256? Well, it works out very nicely for binary numbers, but we could have used 128 or 512. Why 256? This is based on subjective testing, is having people listen to reproduced speech with different quantization levels and asking them to tell us whether they can hear any noise or not. And it turns out that if we reduce the size of the levels so that there are 256 of them in the range of voltages on the telephone system, that reduces the quantization noise below a point where a person's brain can detect it happening. Now, another question is, how often do we have to take samples so that you have enough dots so that when you connect the dots at the far end, what you end up with looks like what you started with? Well, a fellow by the name of Harry Nyquist realized that in order to be able to reproduce the signal, you have to take samples of it more than twice as often as its frequency bandwidth. And this is now often referred to as the Nyquist sampling theorem. I'm not deriving it or anything, I'm just telling you what it is. You have to take samples more than twice as often as the frequency bandwidth of the signal. Now, if that signal that we're using in an example is on a telephone line, do we know what its frequency bandwidth is? Yes, 300 to 3300 hertz, the voice band. That's 3000 hertz wide. So following Harry's theorem, we have to take samples at least 6001 times per second in order to be able to reproduce the signal. Just to make sure there are no problems, we do it more often. We take samples 8000 times per second. How many bits do you need to code a number between 0 and 255 into binary? Well, last time I checked, 256 was 2 to the 8th, and the implication of that is you can represent any number between 0 and 255 using 8 bits. So what we do is we take a sample of the value of the signal 8,000 times per second, and we represent the value of the sample as a byte, 8 bits. So we have to transmit a byte 8,000 times a second from A to B to communicate a voice digitally. Now, if you want to know how many bits per second that is, you have to do the math. 8 8s are 64, and what we end up with is 64,000 bits per second, or 64 kilobits per second for short. And this is called a DS0 in the business. Digital Service Level 0. We've heard of service level agreements before. This is what you're going to get. Well, as far as Bell Labs was concerned, that formalized all this stuff in the 1950s, this was service level 0, the basic unit in the digital hierarchy. So it's called DS0, Digital Service Level 0. When somebody's talking about a channel on a digital transmission system, this is what they're talking about, a DS0, 64 kilobits per second. When they're talking about a trunk, they're talking about a DS0. When they're talking about a phone call, they're talking about a DS0. Now, besides just knowing that a DS0 is 64 kilobits per second, the understanding that's useful to have here is what that 64 kilobits per second actually is a byte that gets transmitted 8,000 times per second. And as soon as you get your mind around that, then you know how all traditional transmission systems work. For each input, they move a byte to the corresponding output 8,000 times per second. It just is a question of how many inputs and outputs they have. On a T1 system, there are 24 inputs and 24 outputs. So what it does is it moves a block of 24 bytes, one from each of the inputs, from A to B 8,000 times a second. On a Sonnet OC48 system, there are 32,256 inputs and 32,256 outputs. And so what it does is it moves a block of 32,256 bytes 8,000 times per second. They all work at the same rhythm, 8,000 times per second. I hope you're reasonably comfortable with this. Nobody expects anybody to be an instant expert in sampling theory, but you have to know about this. If you stay in the telephone business, this is going to haunt you for at least the next 20 years. When somebody says a channel on a digital transmission system, this is what they're talking about. When somebody talks about a trunk being carried on a digital transmission system, this is what they're talking about. When somebody talks about a phone call on a digital transmission system, this is what they're talking about. 64 kilobits per second, a DS0. So that's a DS0, Digital Service Level 0. One phone call, one trunk, one circuit being carried on a transmission system. Do we stop there? Of course not. There's a whole hierarchy of these things. Now, there's nothing magic about these numbers. These are industry standard line speeds. Companies manufacture equipment that works at these speeds. Other companies purchase it, maybe from different vendors, and integrate the equipment together to build networks that run at these speeds. And then they file tariffs with regulators to offer services that run at these speeds. These are just industry standard line speeds. The anchor point on this chart is a DS0, 64 kilobits per second. In traditional telephony, that's one phone call, one circuit, one channel, one trunk. As far as Bell Labs was concerned, the next level up would be service level number 1, a DS1, which is a number of bits per second, which is 1.5 million. Now we could phone up the phone company and say, we want to get a DS1 rate service from this room to the room in the building across the street. They would be happy to do that for us. They've already got all the tariffs filed with the regulator. They've already got all the billing systems built to do this. All the technicians are trained. The stuff is already in the trucks. The wires are probably actually already in place to do this. They would be happy to provide us with a point-to-point, full-time DS1 rate service between two buildings. If we wanted to, we don't have to, but if we wanted to, we could then go buy two multiplexers from some company like Tel Labs or Newbridge, now known as Alcatel, or some company like that, and stick a multiplexer at each end of our 1.5 megabits per second. And what these multiplexers would do would be to divide the 1.5 megabits per second up into smaller pieces. So we could use some of it to connect a PBX in this building to a PBX in that building for doing voice calls. We could use another part of the 1.5 megabits per second to connect a video conferencing system in this building to that one. And we could use the rest of it to connect the computers, the LAN in this building, to the LAN in that building. And if we chose to divide our 1.5 megabits per second up into 64 kilobit per second chunks to break it up into DS zeros, we would get 24 of them. So if you want to think of it this way, a DS1 is the same thing as 24 DS zeros all running interspersed in a high-speed stream. In Europe, they do things differently. Now, actually, when I say Europe in the telecommunications business, that means the rest of the world. Canada, the US, Japan in many respects, half of the Caribbean and parts of the Middle East use American technology. The rest of the world uses European technology. And whereas DS1 used to be called high-speed access in North America, E1 is used in Europe. E1 is 2 megabits per second, and it works out to 32 channels instead of 24. There was another one called DS2. That's obsolete now. You never hear anybody discussing DS2. It was a point of commonality between DS1 and DS3, and it was a stepping stone on the way to DS3, but we just skipped directly from DS1 to DS3 now using Sonnet in North America. And what DS3 is a number of bits per second. It's service level number 3, and it's 45 megabits per second. And this is what the big transmission systems in North America do, is they move multiples of 45 megabits per second around. They move DS3s around. In the rest of the world, the transmission systems do synchronous transport modules, and if you move one of those 8,000 times a second, it ends up being about 155 megabits per second. Now, out of all of this gibberish, what you have to know, DS0 is one phone call in traditional telephony. It's 64 kilobits per second. DS1 used to be called high-speed access in North America. It's 1.5 megabits per second, which is equivalent to 24 DS0s. And DS3 is what the big transmission systems move around. Notice on this chart that it doesn't say anything about copper wires or fiber optics or radio or anything like that. We're just saying how many bits per second you need to do. It doesn't say anything about how to actually do this. Now we're going to take a quick survey of some actual technologies for actually implementing these numbers of bits per second. And these technologies tend to be called digital carrier systems because what they end up doing is carrying multiple DS0 channels on a single high-speed transmission system. Probably the most popular and widely deployed in North America has been the T1 transmission system. And what this is a system that was designed to carry the DS1 rate, which is 1.5 megabits per second, on 4 copper wires. So T1 is the technology, DS1 is the speed that it runs at. Another technology was called T3, and this was designed to carry the DS3 rate, which is 45 megabits per second, again on copper wires, little thin coaxial cables. So T3 is a technology, DS3 is a speed that it runs at. This is the most commonly made mistake in the high-speed circuits business, always referring to 45 megabits per second as a T3. Hopefully not. T3 is a particular method of implementing digital service level 3, 45 megabits per second. It's an old, obsolete way of doing that, and it's been replaced by a shiny new method of doing DS3s called SONET. SONET actually stands for Synchronous Optical Network, and it was designed to carry multiples of DS3s, most often on fiber using the optical carrier system. So an OC1 moves 1 DS3. OC12 runs 12 DS3s. OC48 is widely deployed in North America. That moves 48 DS3s. OC192 is now off the shelf. So it's important to distinguish between the technology and the number of bits per second that it implements. T1, T3, and SONET are technologies. They implement service levels, DS1 and DS3. Those technologies, T1, T3, and SONET from the previous slide, were all mostly oriented towards transmission systems. They move stuff from A to B, and B to A. By the way, everything I say happens in both directions at the same time, but it's a lot easier to explain it just one direction at a time. There's not really any notion in T1 or SONET of going to C, D, E, F, or G. Now there's another set of technologies that also move DS0 channels, but additionally have the capability for you to indicate where you want these DS0 channels to go to. And this set of technologies is called ISDN. What does ISDN stand for? Integrated Services Digital Network is the standard answer. What else does it stand for? I still don't know. Well, it's kind of cheating a bit. It still does nothing. Integration subscribers don't need. Phone companies thought that that stood for I smell dollars now in the 1960s. But most of the time what it actually stands for is it still does nothing. Now there are two stories here, and these are apples and oranges. They're completely separate stories, and we must keep them separate. There's the basic rate interface and the primary rate interface. Let's talk about ISDN BRI, basic rate interface, first. This was intended for residences. If we take a look at this graphic of the public switch telephone network, what's not digital on this graphic? All of the switches are digital. All of the transmission is digital. It's the last 3 miles. The way that we represent information on the loop is still using analog techniques. The whole idea behind ISDN basic rate was that we were going to stop using analogs on the loop. We were going to stop providing plain ordinary telephone service. We have to stop restricting ourselves to the voice band. But instead, what we were going to do is give you a nice integrated services digital network and a basic rate interface to the network. And what do you get with the basic rate? 2 chickens in every pot. They were promising not 1, but 2 chickens in every pot. You get 2 DS0 channels, plus a little signaling channel using a little baby carrier system on the local loop to your house. Phone companies started talking about this in the 1960s. Now, what could my dear departed grandmother do with 2 digital channels access to the network in 1967? Well, she could talk to 2 people at the same time if she could find somebody providing ISDN basic rate service and an ISDN telephone. And people said, well, so? And it never really gained any momentum in North America. Yes, there are little applications for it here and there, but we were supposed to have already all switched over to ISDN basic rate as the new plain ordinary telephone service. That never happened. And now it appears that ISDN basic rate will join POTS on the dustbin of history. There were some pockets of implementation of ISDN basic rate in North America. One of the applications was telecommuting, because in the 1980s, for example, if you wanted to do data communications over a voice band analog circuit, you could maybe do 2.4 or 4.8 or maybe 9.6 kilobits per second using a modem. And that's not fast enough to do client-server computing. However, with the DS0s you get with ISDN basic rate, you can use those for voice or you can use them for data. And actually you can combine them together. So you get 2 times 64 or 128 kilobits per second phone call. And that is enough for doing client-server computing. So there are a number of people who have ISDN basic rate installed in their homes so that they can telecommute. This has all been made obsolete, of course, by DSL. You see, all 3 of these technologies, POTS, ISDN basic rate, and DSL, are all technologies for representing information on the local loop. POTS dates back to 1874, and using modems, we can move at most 53 kilobits per second on a clear sunny day. ISDN basic rate dates to 1964-65, and you can move 128 kilobits per second. The kind of DSL that I have installed in my office, that dates from 1998 when the technology was deployed, and I've got 3 megabits per second. So already that's 24 times faster than ISDN basic rate on the same physical wires. ISDN primary rate is a completely different story. Basic rate specifies pulses on 2 copper wires. Primary rate doesn't specify the actual physical connection. It just says that you need a 1.5 megabit per second connection to run ISDN primary rate. Most of the time that would have been a T1 circuit, but you could implement it on fiber or radio or whatever you want. ISDN primary rate is more of a service that has to do with being able to exchange control information. What ISDN PRI does is takes that 1.5 megabit per second physical connection between you and the phone company, and it divides it up so that 23 out of the 24 channels, remember 1.5 megabits per second is the same thing as 24 DS0 channels from the previous discussion. It makes 23 out of 24 channels usable for communicating voice or data back and forth between you and the phone company, but it reserves the 24th channel for signaling control information between you and the phone company. And the set of control messages, for those of you like details, is called ISUP, the ISDN user part. These would be the control messages that a call center could use to tell the telephone company's SS7 network, stop sending phone calls here, we're busy, reroute those 800 numbers somewhere else. There are lots of examples of where ISDN PRI control commands can be used. The whole idea here is to allow customer control of their network and be able to change what the DS0s are for and where they go. For a while, for example, internet service providers, when they have dial-up access points, they would get a T1 going to where the actual equipment was that people phoned into, but they would pay extra for the PRI service because what that allowed them to do was on the fly increase and decrease the number of those channels that were actually in service. And so they could optimize how much they were paying for communications versus how many busy signals people got trying to dial up at that access point. That's just another example where PRI is used. If you've ever heard the term PRI trunk, what somebody means when they say PRI trunk is a DS0 channel that has an ISDN PRI associated control channel and control information and commands. So to summarize, ISDN basic rate is 2 channels, 2 wires to residences. ISDN primary rate is all about control messages back and forth between your corporate organization and the phone company. To finish off this part, let's take a higher road and look and see what you can actually do with these transmission systems. One thing you can do is voice. Now this is pretty obvious stuff because all of these systems were designed to move digitized voice around. Any kind of voice communications you can think of can be carried on channels on a digital transmission system. Regular dialed phone calls, watts, which is volume discounts, but we couldn't call it VD service for obvious reasons. And even some of the older services like tie lines that were dedicated connections between PBXs, all of this stuff can be carried on channels on a digital transmission system. In this graphic, what we're trying to illustrate with the A's and the D's is that at home, I've got an analog access line. So that means that the digitization happens on the line card in the switch in the CO to which I'm attached. Now at work, it's possible that you might have a digital connection to the telephone switch. And what that means is that there's a chip inside the telephone that does the voice digitization, just as we discussed on a previous slide. This chip is called a coder/decoder, or codec for short. And the way it would work is in a digital telephone, you have the speaker and microphone in the handset, and on the cord going from the handset to the telephone, there would be a continuous voltage, which is an analog of the sound pressure waves coming out of your throat. But inside the telephone, there's the codec chip that does the analog digital conversion. So on the wires coming out of the telephone, there would be pulses representing the digitized speech. Can you make a phone call from an analog telephone to a digital telephone? Well, yes. But how can you do this? I mean, these are two fundamentally different ways of representing information. Well, obviously, because we can convert between the two, and we've got a standard. This 64 kilobit per second DS0 was developed by Bell Labs in the 1950s, and somehow they got every telephone company and every telephone equipment manufacturer on the planet to go along with their scheme for voice digitization. And this is an international standard. So whenever we're talking about exchanging information between telephone companies or between different networks in traditional telephony, we're talking about DS0s. However, if we're not talking about interoperation between networks, we're talking about a story where you have both ends of the circuit, then you can do whatever you want. You don't have to use this standard. You could use something that was more efficient. And there are older technologies that do 4-to-1 compression. 4-to-1 compression means that instead of using 64 kilobits per second to code the speech, we only use 16 kilobits per second. And 16 is 1/4 of 64, so what that means is you could now fit 4 phone calls into one DS0 transmission channel, so people call that 4-to-1 compression. With some of the newer codecs like G.729, and we go through all of the codecs in the voice over IP series because that's where they're being used, we're getting down to 8 kilobits per second and maybe even less. and that would be 8:1 compression, without much degradation in the perceived sound quality. Another example where we do not use the 64 kilobit per second standard is on cell phone networks. When you're using a cell phone, you're not talking directly onto the public telephone network. You're talking on a private radio network that Verizon Wireless has built. And they can do whatever they want on this radio network. And it depends what generation of phone you're using, but on their network, your phone is transmitting to the base station at 11 or 13 kilobits per second. What else can you do with a digital transmission system besides voice? Well, you can do data. We include this discussion here for completeness. There's a whole nother video course that covers this topic in an entire video. But for completeness, we'll just go over the main ideas here. We traditionally divide data into legacy traffic and newer client-server wide area network stuff. Let's talk a little bit about legacy traffic. What's a legacy? Well, sorry to break the bad news to you once again, but when you shuffle off this mortal coil, you cannot take your earthly possessions with you. You must legate them to somebody who remains on the planet after you've gone off to the happy hunting grounds. So when we use the term legacy system or legacy traffic in this business, what that means is that the people who decided to buy that IBM mainframe computer in 1974, they're all gone now, and they left it to us to deal with. Usually what we're talking about when we say legacy traffic is subrates. And subrate means anything below 64 kilobits per second. And there were some industry standard subrates like 2.4 and 4.8, 9.6, 19.2. And these would traditionally be associated with dumb terminal to remote host connections. Fax machines also fit into this category. They run at 9.6 or 14.4 kilobits per second. And it's quite easy to show how you could get a special card to plug into your multiplexer called a subrate multiplexing card that would allow you to combine multiple subrate connections onto one DS0 transmission channel. And you can show that you can do 5 9.6s on a DS0, or you can do 10 4.8s, or 20 2.4 kilobit per second subrate connections. For newer stuff, we're usually not talking about dumb terminal to remote host communications. We're talking about computer-to-computer communications, client-server computing. And usually what we would do is connect all of the stuff in this building using LAN technology, and all of the stuff in this building using LAN technology. And then we would use quite a few channels combined together to make a high-speed connection between the two LANs. And when you connect two LANs together, that forms a WAN, a wide area network. What else can you do besides voice and data over a digital transmission system? Well, you can do video. Now, as soon as I say digital video, one has to say, well, what kind of digital video? Because when we're talking about digital video, we're always talking about compromises and trade-offs, particularly between the size of the picture and how often it's refreshed versus how many bits per second you have to transmit to actually transmit this picture. So we're talking about compression and codecs here, versus the number of operations per second you have to do on a processor to implement that level of compression. And it's easy to squeeze two of these factors, but it's hard to squeeze all three at the same time. Let's take a look at each of these factors one at a time. For picture size, there are a number of standard digital video picture sizes. One of the older ones is called CIF, Common Interface Format. And this is a pretty small picture size, 352 by 258 pels. Pixels are called pels in the digital video business, stands for picture elements. And Common Interface Format would have been supported by older video conferencing systems. Since there was not a lot of capacity available in terms of bits per second, we had to reduce the size of the picture. Right now, in North America, standard definition is considered to be 720 by 480. If you go to Blockbuster Video and you rent a DVD, what you're getting is an image that's 720 pixels across by 480 pixels down, and that's called SD, standard definition. Of course, we're moving to high definition, although 100 years from now it won't be called high definition. But it's called high definition right now, HDTV. And there are a couple of different flavors that are being pushed by different manufacturers and interest groups. We've got two main sizes, 1280 by 720 and 1920 by 1080. These are the two picture sizes for HDTV. You'll also see I's and P's after this. I means interlaced. For historical reasons, we used to draw the picture in two parts. First we'd do every second line, and then we'd go back and fill in the lines in between. We don't need to do that anymore. Processors have improved since the 1940s, and now we can draw the lines sequentially down the screen. That's called progressive. The problem with interlacing is that you're only drawing a line actually at half of the refresh rate of the screen. And so if a line, a graphics line, sits on top of a television line, but it's only on one of the line, it's not two lines thick, it'll look like it flashes on and off because the eye can pick up flashing at 30 times a second, which is what you get with interlaced in North America. With progressive, you get 60 pictures per second, and so we don't have so much of a problem with things flashing on and off on the screen. Another factor is compression. In other words, reducing the number of bits per second that come out of the camera to some manageable number that we could store on a disk or on a tape or on a hard drive or transmit over a network. Now, we're always interested in using standard techniques for doing compression so that we could, for example, in the Telecom video studio, take this video you're watching right now and compress it using a standard technique, record it onto a digital versatile disc, a DVD, mail it to you, and then your video equipment would have the same compression technique algorithm in it, so it could understand the ones and zeros recorded on the DVD and recreate a picture that you're looking at right now. As far as standards for compression, we're talking about codecs, decoders here. The Moving Picture Experts group has been dominant in this field for the last while, and they come up with what they call phases of standards for some reason. MPEG-1, that's MPEG Phase 1 standards, was coding of video at 1.5 megabits per second. And this was designed for video CDs. Now that's not very interesting. We moved on to MPEG-2. And MPEG-2 allows you to specify how many bits per second you use to code the image. Of course, the more bits per second you use, the better the quality, but the shorter length that you could record on a fixed size disk. Usually we're talking about 3 to 4 megabits per second. What you're watching right now is coded in MPEG-2 at about 4.1 megabits per second. We have to adjust it a little bit to fit it onto the disk. When you go to the video store and you buy a DVD, you're getting a piece of plastic with MPEG-2 video recorded on it. When you sign up for TV, like DirecTV, you're getting MPEG-2 over the air, over a radio channel with modems delivered to your home. So this is what we're using today. We probably will be moving on to a new standard for compression called H.264. And the great thing about H.264 is you get the same quality for 1/3 the bits, and it recovers better from errors. The reason why we didn't use H.264 before was because of the processing requirement. All this stuff requires many, many mathematical operations to be implemented on a processor, and we want to do it in real time, so we can pull the MPEG-2 encoded stuff off the DVD, decode it, and create a picture while you're watching it. And you couldn't do H.264 in real time up until recently. But with the advances of digital signal processors and having parallel processors, we can now do the H.264 compression and decompression algorithm in real time. So this will probably end up replacing MPEG-2, and watch for it from a telephone company near you soon when they go into the IPTV business. They might start off with MPEG-2, they might start off with H.264. Besides these three factors, the picture size, the compression technique, and the number of operations that have to be done to implement the compression technique to be able to move that picture size around, the transmission networks for video are evolving. Traditionally, it has been analog channels, whether it's on a cable TV system or from a satellite. Those are analog radio channels or analog channels at radio frequencies on a coaxial cable. If you want to do digital video over those, you have to stick modems on the channels to move the digitized video over the analog system. We're going to be moving, of course, to IP packets, and all video will be carried in IP in the not too distant future. For connection control, there's been quite an evolution, and it's not over yet. Originally, you had to have dedicated lines. Then, of course, we moved to ISDN, and a lot of systems use 6 channels. 6 times 64 is 384 kilobits per second. So you could have a picture-tell video conferencing system between your buildings. Then, for connection control, we stopped using ISDN so much, and maybe we started using the H.323 family of standards with IP packets. And there's a connection control standard called H.225 in there that could be used for video conferencing. That was implemented by NetMeeting from Microsoft. This is now obsolete, and where we're headed with that story is SIP, the Session Initiation Protocol. And this is what will be used to set up video communications over IP networks for everything. For regular television, for video on demand, for pay-per-view, for video phones, for video conferencing. It's all going to end up being IP packets and control via SIP, the Session Initiation Protocol. We certainly cover SIP in the Voice over IP series. We do all of this stuff at the same time on a single transmission system. It's not like there's one fiber backbone for voice and a different one for data and a third one for video and a fourth one that's the internet. No, it's all run over the same piece of glass. And what we do is take multiplexers and use them to divide the capacity of the transmission system so that we can allocate some of it to connect voice equipment here to voice equipment there, some of it to connect data stuff here to data stuff there, some of it to connect video stuff here to video stuff there. This is the telecom business. They're buying wholesale and selling retail. Now this picture actually exists at 2 different levels of magnification. This could be a picture of the telephone network. On the left is your home phone connected to a central office switch and then going over trunks to the central office switch to which my phone is attached. This same picture also exists at an enterprise or organization level. This could be two locations of your organization connected together with a high-speed service provided by the telephone company. And you could be doing the same thing. You could use a multiplexer at each end to divide the capacity up into different pieces. So you could use some of it for voice, some of it for data, and some for video conferencing. So it's the same picture at two different levels of magnification. In this part, we're going to drill into the technology a little bit deeper to understand channelized multiplexing. And yes, the network is moving to a packetized system. However, there's still a huge installed base of channelized stuff around, so you still have to know about it. We certainly will talk about packets and statistical multiplexing, but that's in an upcoming DVD in this core training series. Here we're going to concentrate on channelized multiplexing. In traditional digital transmission systems, what we want to do is connect many users onto the same transmission system so they can all use it at more or less the same time. We do not use the technique that's used in cable TV. With cable TV, there's this huge frequency band available, and what we do is divide it up into smaller frequency bands called channels, and then we stick video pictures in each one of them. And if you want to watch one of those video pictures, you need a tuner or a converter that's going to go grab the video picture that you want to watch at the frequencies it's at on the cable and downshift that down to the channel that's being displayed on the screen of your television. So what's happening there is each video picture is getting to use a portion of the overall capacity of the circuit all the time. We do not do that in digital transmission systems. In a digital transmission system, each user gets to use the entire capacity of the circuit, but just for a very short interval, for a short period of time. And then they have to get off and somebody else can use it. So in a digital transmission system, we end up sharing a single circuit in time. So it's a type of time-sharing system. What's an example of a time-sharing system? Well, how about timeshare condos? What's a timeshare condo? Well, you, along with 51 other people, all sign up for the right to use the condo for 1 week. But this is a very strictly ordered system. You can't just go to the condo whenever you feel like it. You have to wait until your week happens. And then when your week finally happens, you have the right to move in, unpack, and you have full and complete enjoyment of the entire thing for 1 week. And then at the end of the week, you have to pack up and leave, and the next people can move in and use the whole thing. Well, let's change the time scale a little bit here. Let's say that you get to move in, unpack, and you have full and complete enjoyment of the entire facility for 24 hours. And at the end of your 24-hour long time slot, you got to pack up and leave, and somebody else can use it. We call these things hotels. Well, let's change the time scale even a little bit more. Let's say that you get to move in, unpack, and you've got full and complete enjoyment of the entire facility for 7/10 of a microsecond, 700 nanoseconds. And at the end of your 700 nanosecond long time slot, you got to pack up and leave. Well, this is the rate at which we're talking about sharing things and the length of time you have to use it if we're talking about the DS1. Remember, digital service level 1, that was 1.5 megabits per second. Well, by definition, that means that each bit gets 1 over 1.5 times 10 to the 6th seconds in order to indicate whether it's a 1 or a 0 to the other end. And then it has to get off, and the next bit's got 1 over 1.5 millionths of a second to indicate whether it's a 1 or a 0. And that works out to 7/10 of a microsecond. You want to talk about 45 megabits per second? Then each bit has 1/45th of a microsecond available to indicate to the other end, is it a 0 or is it a 1? Then it has to get off, and the next bit can use the circuit. So the way that we get more bits per second on a digital transmission system is to share it more often, to get on and off faster and faster and faster. And the length of time that each bit has available to indicate whether it's a 0 or a 1 to the other end just keeps getting shorter and shorter and shorter. And we passed a billionth of a second off the shelf quite a long time ago. This idea of taking a facility or a circuit and dividing it up into fixed sized chunks and then assigning a user to each chunk is called channelizing a circuit. In the timeshare condos business, the standard chunk size is 1 week per year. In the digital transmission business, the standard chunk size is 64 kilobits per second. So we would organize things so that after everything's said and done, each user on the digital transmission system had the ability to move 64,000 bits per second from one place to another. This traditionally has been for voice communications, where we reserve a fixed amount of capacity, 64 kilobits per second, on the transmission system for a phone call. And if we start thinking, how efficient is that? Well, during a phone call, how often is noise coming out of your face and how often is nothing coming out of your face? Well, we could think that we're supposed to be polite, so half of the time you're listening. So right there, during a phone call, 50% of the time noise is coming out of your face, 50% of the time nothing is coming out of your face. And then with maybe all of the pauses between the words and stunned silences and things like that, maybe we're down to 40% of the time noise is coming out of your face, 60% of the time nothing is coming out of your face. And yet we're reserving this 64 kilobits per second for you on the network all the time, whether you're saying anything or not. 40% occupancy, that's not so bad. For data communications, though, the statistics are way worse. I would claim that when you're doing things like email, the vast majority of the time, you're doing nothing with your communication circuit. You're reading the email on the screen, or you're pressing keys on the keyboard. And it's not actually until you click send that you're actually using the communication circuit. I would claim that more than 99% of the time when you're doing email, you're not actually communicating anything. So this idea of reserving channels for data communications never sounded like such a good idea, because most of the time we'd end up doing nothing with this communication capability, even though we had capacity reserved for us on the network. So there was always a different idea for data communications, where we wouldn't reserve capacity for you. Instead, we would give you capacity on demand, or bandwidth on demand. And the idea is, we don't have anything set aside for you in the network. You just have a possibility of transmitting stuff across the network. And if you actually do have an email message to transmit, we'll send it in the next available time slots. But if you don't have anything to transmit, somebody else can use those time slots. So it becomes much more efficient when 99% of the time you're doing nothing with your communication possibility. What I'd like to do is to get channelized multiplexing, where we have capacity reserved for your communication session. I'd like to get that under our belts first, and then we'll look at bandwidth on demand as a value-added story built on top of this. Bandwidth on demand would be implemented by doing something like taking two routers and connecting them together with a reserved channel, but then connecting up a lot of people to these routers on each side and letting them send packets across the channel whenever there's a free spot. So I'd like to look at channelized multiplexing and understand that first, and then in an upcoming course we will certainly spend a lot of time talking about bandwidth on demand and packets and some of the technologies used to implement it, like frame relay, ATM, IP, and MPLS. On this slide and the next, we're going to take a quick look at the T1 carrier system. Now, this is fairly old stuff and slow stuff, and if you're not interested, just press the skip button to go to the next discussion. However, there are two reasons for understanding T1. One is that it lets us understand what a multiplexer is and what a multiplexer does, and the idea of channels and how we sort out what's where. The second is that once you understand how T1 works, then you know how Sonnet works, because it's all the same stuff, just a different scale. A first question to ask is, what does the T in T1 stand for? Its official name is the T1 carrier system. What is it carrying? Trunks! It's the trunk carrier system number 1. If you remembered nothing else about T1, remember this: it was designed to increase the density of money on the circuits between central offices. Well, if you want to be a little less crass, you could say it was designed to leverage the installed base by increasing the circuit density on it. Before there was digital anything, there were analog trunks. What's the difference between an analog loop and an analog trunk? Well, not much. Loops are 2 wires, trunks were 4 wires. Presumably loops are 2 wires when you used them in both directions at the same time, because everybody had one, so they had to be fairly cheap. Trunks are 4 wires, where you use 2 wires in each direction. If you use twice as many wires, you get slightly better sound quality. And presumably, since these are shared and there aren't as many of them, we could spend more money on them and use more wires. But other than that, analog loops and analog trunks are the same thing. We put a voltage on them, which is an analog of the sound pressure waves. How many simultaneous long-distance phone calls can you do on an analog trunk? 1. We're putting voltage analogs of sound pressure waves on there. Only one person can do that at a time. Now, what do you think the people in the finance department at AT&T said when the folks at Bell Labs said, hey, we came up with a way where you can carry not one simultaneous long-distance phone call on those circuits. We came up with a way where you can carry 24 simultaneous long-distance phone calls on the existing circuits. Well, they probably said ka-ching. And how much is the equipment going to cost? Because what we have to do is stick a multiplexer at each end. And what the multiplexer is going to do is take 24 analog trunks, digitize the information on there, combine that all together into a DS1 rate stream, 1.5 megabits per second, and transmit that digitally using pulses over the copper wires. And then we need a multiplexer at the other end that's going to break this back out to 24 analog trunks. The 2 central office switches don't know from T1. All they see is 24 trunks leaving here and 24 trunks arriving over there. But in the middle, we take that information and move it over a single 4-wire copper circuit. So we're increasing the density of circuits by a factor of 24 on the existing wires. We don't use T1 for connecting central offices together anymore. We've got way better stuff. We use fiber optics now. T1 has migrated in our model from being a transmission technology to being an access technology. T1 is used as the physical access wiring for a lot of services, the stuff that goes from your building to the nearest central office. It's used for dedicated T1s. It's used for ISDN primary rate. It's used for frame relay as the physical wiring, and it's used for all sorts of different IP services. This is technology that dates from 1958, and it carries 1.5 megabits per second. It will disappear, but there's a huge installed base to deal with in the meantime. Here we're going to take a look at the main components of a channelized time division multiplexing system using T1 as an example. The components are a multiplexer at each end, channel service units, and repeaters. Since T1 was designed to carry 24 trunks, that means that a T1 multiplexer is going to have 24 ports on it. And a port is a term for a physical connection, a hardware connection, usually on a piece of equipment. So we'd be able to plug on 24 circuits onto this multiplexer, and it would take the information off of them and combine it into a high-speed stream, 24 times 64 kilobits per second. And if you add a bit of overhead, it comes up to 1.544 megabits per second, which is the number of bits per second on a T1 system. Then we've got the channel service unit. And the channel service unit is a device that actually represents these ones and zeros on the copper wires, which are the T1 circuit. And in an upcoming slide, we'll see the technique, how it uses pulses to represent ones and nothing to represent zeros. We need repeaters on a T1 system every 6,000 feet, and we're certainly going to discuss those coming up. And then at the other end, we've got a channel service unit and a multiplexer. And the idea is that the multiplexer at the far end is going to break out the information it's receiving and put it on the appropriate port. This is the simplest implementation. What goes in on port 1 comes out on port 1. What goes in on port 2 comes out on port 2. There's no crossing over or combined channels or anything like that in this picture. This is just the simplest implementation. The way that this works is that the T1 circuit is a timeshare condo. First, port 1 on the multiplexer gets to use the T1 circuit to transmit a byte. And then the multiplexer at the far end puts that on port 1 output. Then port 2 gets to use the T1 circuit to transmit a byte. Then port 3 all the way down until the last one, port number 24, transmits a byte. And then we start over again. And we go in a strict order, one after another, no skipping your turn, no taking 2 turns, sending 1 byte at a time. We have to go through the order 8,000 times per second. Because remember, what we're doing is DS zeros here, 64 kilobits per second, and that means we have to move a byte from this input to that output 8,000 times a second. We also have to move a byte from this input to that output, this one to that one, this one to that one. We have to move a byte from each input to each output 8,000 times per second. So it's going to move 24 bytes 8,000 times per second to the other multiplexer, so that each of those channels end up getting 64,000 bits per second. There's a couple of nasty details about T1. We could spend a whole 2-day course talking about T1. I've actually been to a 2-day course on T1. It wasn't very interesting. Why don't we do the 5-minute version instead? There are 2 main questions to discuss here. One of them is, at the far end multiplexer, how do we sort out what goes where? And then the other question is, how do we represent the ones and zeros actually on the copper wires? What we're discussing here is how does the far end multiplexer sort out what goes where? Let's say you're a T1 demultiplexer in New York City. Somebody has to do it. What you've got is a circuit with 1.5 million bits per second screaming down at you. How do you know which bits go on the output for port 1 and which bits go on the output for port 2? Well, we simplify things, because remember the T1 is a timeshare condo. First, port 1 gets to transmit a byte, then port 2 sends one, then port 3, in a strict order, one after another, and then the order repeats. So we know that the information going across the T1 circuit, there will be a byte for channel 1 or port 1, there will be a byte for port 2, there will be a byte for port 3. But still, how do you know where the boundaries of the bytes are in this stream of bits? And how do you know that this is the byte for channel 1 and this is the byte for channel 2? It's the same problem you would have if you went to a high school baseball game and arrived late. How do you know where they are in the batting order? People get up to bat, and we go through the players on the team in a strict order, the batting order, and when we finish the order, we start over again. But if you arrive late at a high school baseball game, how do you know where they are in the batting order? If at this baseball game, when they finished the batting order, so everybody on the team had batted, and then we're going to start over again, they sent a kid waving around the bases, waving an orange flag, then all you would have to do if you arrived late is sit back and wait, and when you saw a kid run around the bases waving an orange flag, you'd know that the next batter up was batter number 1, right? That's what we do here. We send a byte from each port, and then a little marker saying finish the batting order, gonna start over again. Byte from each port, little marker. Byte from each port, little marker. So the problem at the far end devolves into finding this little marker, and as soon as we find it coming down the line, we know that the next 8 bits that come down the line go on port 1, the 8 bits following that go on port 2, the 8 bits following that go on port 3, and so forth. What is this marker? Well, it's a single bit called the framing bit. If you wanted to draw a picture of what I've been speaking, you would probably end up drawing a picture that looks like this, where we've got little boxes with letters inside them and numbers above them, trying to represent the groups of bits on the T1 circuit in time. And what we have is a byte from each of the ports with a framing bit, 1 bit long, sitting in front of it. And that collection, a byte from each port and a framing bit, is called a frame in the transmission business. And we send one of these down the T1 circuit 8,000 times per second. Because remember, we have to send each byte within that frame 8,000 times per second. Because 8 8s are 64, we need to do 64,000 bits per second for each of those ports. Now you might be thinking, what good is one framing bit? It could be either a 0 or a 1. It looks just like all of the data bits. It's not painted orange. And you'd be right. One framing bit is not very useful. Don't we need some sort of like pattern of bits that we could recognize at the far end? And the answer is yes. But in the T1 system, they got pretty clever. Instead of putting the pattern all together as a clump at the beginning of the frame, what we do instead is consider a number of frames in a row to be a larger unit. Then we don't just have one framing bit, we've got a bunch of them, but they're not all together in a clump. They're spread out, one at the beginning of each of the frames. And in fact, what we do is we consider 12 frames in a row to be a larger unit called a superframe. Then we have 12 framing bits, but they're not all together in a clump. There's one at the beginning of each of the 12 frames. And at the transmitter, we have a standard 12-bit long pattern called the framing pattern, and it inserts a bit of the pattern in each of the framing bits of the frame. So the first bit of the framing pattern goes in the first frame, the second bit of the pattern goes in the second frame, the third bit goes in the third frame, and so forth. Now we're starting to get somewhere. At the receiver, when we first turn our power on, We know that the T1 frame is 24 bytes with one framing bit. That's 24 times 8 plus 1. It works out to being 193 bits long. So at the receiver, what we would do is we would bring in some data and then we would look every 193rd bit and say, do we see that standard framing pattern sitting in the data? Now, chances are very good the first place you look, the answer is no, because you're not looking the right place. So you shift over one bit. Do I see it? No, 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 no. And all of a sudden, click, you're going to lock on and see that framing pattern sitting in the data. You just found the little orange flag. Is it possible that the pattern is accidentally replicated in the data? Yes. So what we do after we think we found it at the receiver is shift over 12 frames. Do I see it again? Do I see it again? Do I see it again? And after 5 times of finding the framing pattern sitting in the same bits, we're pretty sure that we found the framing pattern. And at that point, a light would go on the far end multiplexer saying frame synchronization achieved. And at that point, all of the stuff coming out of the outputs at the far end multiplexer would be valid. Up until that point, it's just garbage coming out of the outputs. This technique of using 12 frames was called super frame format or D4 format after a channel bank made by AT&T. And there's an improvement called extended super frame format where we don't actually use all of the framing bits for framing. We use some of them for an error check and then some of the other bits for reporting the results of the error check back and forth. The other nasty detail about T1 is a method for representing the ones and zeros digitally on copper wires. The technique that's used is called AMI, alternate mark inversion. I guess mark is an old word from the telegraph business, meaning active condition. We had marks and spaces. Mark is also an old word from the carnival business, but we're not talking about that use here. What it means is that ones are represented as pulses, zeros are represented as nothings, and the pulses have to alternate, plus, minus, plus, minus. But a pulse is always meaning a 1, regardless of whether the pulse is a positive voltage or a negative voltage. Why would we make the pulses alternate? Well, it makes the average value of the voltage 0, which is important if you don't want to blow up field technicians. It makes it easier to see the transition between two pulses, and it gives us a little bit of free error detection. You see, the rule is they have to alternate. So if, due to some unfortunate circumstance, we lost a pulse during transmission, the far end would see 2 positives come in a row if we say lost the negative that was in the middle. And as soon as they see 2 positives in a row, they know that something went wrong. So it gives us a tiny bit of free error detection. Other than that, it doesn't make any difference. Ones are pulses, zeros are nothings. Now, what's so great about pulses? And why do we need repeaters? Well, to understand what's so great about pulses, let's go back to the analog story. And we can also understand more about the maximum loop length here. The idea with analog is that we put a voltage on the wires, which is a representation of the sound pressure waves. But because the wires are not perfect, they have some resistance to the flow of electricity through them, that voltage will drop with distance away from the transmitter. So if you went and measured the voltage on the wires on a telephone line, the further you got away from the central office, the lower the voltage would be. And this effect is called attenuation. Now remember, the other thing about telephone lines is that they're loops and they act like loop antennas. Even though we put plastic on the wires and twist them together, they still do pick up noise. And that noise adds onto the signal, and once it's on there, you can never get rid of it. Now, after we go a certain distance, 18,000 feet, across a local loop, the voltage would have diminished or attenuated to the point where the far end person wouldn't be able to hear what you were speaking. What happens if we want to go 20,000 feet? Well, we have two choices. One, we could use thicker wires that have lower resistance, but that's real expensive and hard to manage, and like the wires droop on the poles more, for example. What we would probably do is put an amplifier on the line. An amplifier is a booster. It just takes whatever voltage is on the input and multiplies it by a fixed amount. So we would go down one cable segment and then boost the voltage back up, and down another and boost the voltage back up, and so forth. This is all fine except for the noise. Because when the noise is added to the signal and then you want to boost up the signal, you are obliged to also boost up the noise. This is the ultimate problem with analog transmission, is that the transmission system both attenuates the signal and adds noise to it. Then when you want to send the signal down the next cable, you have to boost up the signal and the noise. You go through three of these things the way this is drawn, you wouldn't be able to hear what the other person's saying. You just hear because the noise would be boosted up by each of these amplifiers. Now let's look at pulses. And on a T1 system, we're talking about voltage on those same copper wires. The same thing is going to happen to the pulse. It's going to get attenuated. Its voltage is going to get lower and lower. It will have noise added to it. And the corners will get all rounded off due to the capacitance of the wires. And we have to do something to that pulse after a while to be able to send it further down the line. What do? Stick it through an amplifier and boost it up? No. We stick the pulse through a repeater. What's the difference between an amplifier and a repeater? A repeater is a binary device. It gets to look at the incoming line and say, is a pulse happening, yes or no? There aren't any other choices. And it might look at the incoming line and say, yeah, I can see there's a pulse there. It's pretty small, noisy, and the corners are rounded off, but I can see that there's a pulse there. So it's going to make a decision on the input and say, yep, I'm making the decision, a pulse is arriving. On the output, it's going to generate a nice new clean square pulse to go down the next cable. So compare the two. In an analog system, we boost the noise up to transmit the signal down the next cable. In a digital system, we throw the noise away and just send a nice clean copy of the signal down the next cable. This is the huge advantage of digital over analog. If somebody walks up to you and says, we've got a T1 going from here to Albuquerque, they're lying. Right in your face, they're saying they're lying to you. They don't have a T1 going from here to Albuquerque. They've got a T1 going from their place to their phone company's nearest central office. At that point, the information is taken off of their copper wire T1 circuit and multiplexed together with a whole bunch of other people's data to form a high-speed stream, which is carried over fiber optics to Albuquerque. And in the Albuquerque CO, their information will get picked out of this high-speed stream on the fiber and put on some cheesy copper wire system developed in 1958 called T1 to deliver it 2 miles down the road to their building in Albuquerque. On this diagram, there are some buzzwords written on here. It says 10 mux at the customer premise and 31 mux at the LEC. A 10 mux is a box that multiplexes between DS0 and DS1. So this would be at the customer premise because T1 is a DS1 rate service. The customer gets a DS1. So they would have a multiplexer that lets them split out that DS1 into individual DS0s inside their building if they wanted to. Now the transmission systems move multiples of DS3s, as we said in a previous slide. So at the LEC, at the phone company, they're going to have a multiplexer called a 31 mux that takes DS1 services from lots of different customers and multiplexes them all together into a DS3 stream for transmission. And then it will be carried long distance via an inter-exchange carrier. The LECs and the IXCs interconnect at the DS3 level. T1 is an access technology. It's just used for the last couple of miles down the road. And interestingly, if somebody says we've got a T1 from here to Albuquerque, it's entirely possible there's absolutely no T1 technology involved in that at all. Because remember, T1 needs repeaters every 6,000 feet. And what happens if the access circuit down the road to the central office is more than 6,000 feet? The phone company is going to have to put a repeater on the access circuit. They don't like that. It's expensive to maintain as much as anything else. So there are other technologies that are used to implement these access circuits. There's one called HDSL, and by the way, that has nothing to do with residential DSL. It's similar but completely different. And there's HDSL2, both of which let us do T1 access circuits with no repeaters. One of them works up to 12,000 feet with no repeaters. So it's possible when somebody says we've got a T1 going from here to Albuquerque, they have no T1 at all. They've got HDSL access, SONET fiber transmission, and HDSL access in the far end. It would be far more precise for them to say we've got a full period, that means connected all the time, full period DS1 rate service from here to Albuquerque. That would be completely accurate. In the previous slide, we talked about how we've got copper wire T1 or HDSL for the access, and then it's carried over fiber to Albuquerque, and then copper wires for the access in the far end. Why do we use fiber optics for the long distance transmission? Well, there are three main reasons for using fiber optics, and these are capacity, capacity, and capacity. You can move enormous numbers of bits per second over fiber optics. The cost per bit per second using fiber is lower than anything else you can think of. It's way lower than copper wires or radio or anything like that. So we're always talking about using fiber as the medium for transmission. And as time goes on, we'll be using fiber for access more and more. Individual fibers are bundled together and wrapped in different ways to make up cables, which are actually laid in the ground to go from one city to another. But if we look at the beginning of this story at an individual single fiber, an individual fiber has three main components. It's got the core, the cladding, and the coating. The core is very pure silica glass. The cladding is more glass deposited around the core, but the cladding has slightly different transmission properties for light. The reason why we do this is the way that most of these systems work is you take a laser, this is something that produces light of close to a single pure frequency, and for example, to indicate a 0 to the other end, you turn the laser on. To indicate a 1, you turn the laser off. That's all there is to it. It's light on, light off on fiber optics. It's how many times per second you can turn the light on and off is the interesting part. We passed 1 billion times per second off the shelf quite a while ago. The idea with the fiber is that the core is going to be the guide for the light. The reason why we use glass as a guide for light instead of, say, air, for example, is that glass is very stable stuff. It doesn't kink if you bend it a bit. You don't get turbulence in it like you do in air when it heats up. The dimensions are fixed, and other properties like that make it a good guide for the light from here to there. Since the core is acting as a guide for the light, we want to make sure that all the light stays in the core. And the way we do that is we put another kind of glass called the cladding around the core. And the cladding has a different transmission characteristic for light, so that when the light is shone into the core below a certain angle, we get reflection off the boundary between the core and the cladding. You can see an example of this with a puddle on the street. If you look straight down, you get transmission right through the puddle. You can see through the boundary between the air and the water. You can see the pavement below. But if you bend down and you look sideways, if you get to low enough of an angle, you're going to get a reflection off the surface of the water. You'll see a reflection of the sky. And what we have here is, because the air and the water have different transmission properties for light, if the angle of incidence is below the critical angle, we get reflection instead of transmission. So what we're doing is we're using this glass cladding to put a mirror all the way around the core to keep all of the light in the core. And if you were able to look down the core of a fiber optic cable, don't do this, you could poke your eye out, but if you could do that, you'd see a silver mirror all the way around the core. In addition to putting a mirror around the core, we have to put a plastic coating on there for identification. They've got different colors, and also to waterproof the glass. Because water can actually infiltrate into glass, and even worse, it can carry nasty chemicals with it that can make the glass cloudy, which we definitely don't want to have happen. What we'll then do is take these fibers and start bundling them together. And each cable often is designed on a cable by cable basis, depending on where these fibers, where they're going to drop some out physically out of the cable. So we'll decide how to bundle them together, how we're going to have things connected, and which ones are spares and so forth. But we'll have bundles of fibers together inside the cable, and then we will have waterproofing for the cable, and often there will be a watertight and airtight part in the middle with then exterior coverings on top of that. In a lot of cases, these cables are actually pressurized. We maintain a positive pressure in the cable to keep water out as much as possible, and also so we can alarm it if it gets cut. The pressure is going to drop drastically when the cable gets cut, so we can have an alarm on that. In addition to having the waterproofing, then we've got layers and layers and layers of mechanical protection, steel and plastic, to protect against a type of signal degradation on fiber optics known as backhoe fading. What's backhoe fading? Well, that's when the construction crew digging up the street with a backhoe says, "Cable? What cable? I don't see any cable." And go, and like this, 32,000 long distance circuits go down. Now we can make it difficult for people to cut that fiber with a shovel. For long distance circuits, the fiber is usually buried in the ground about that deep, about 20 feet off the edge of the road. And sometimes you can actually see crews in there with a digger where it digs a trench, and then we lay the cable in and it pats it behind, and it looks all fairly easy until they get to an overpass, and then they have to drill underneath the overpass to get the cable through. But those ones will put layers and layers of plastic, and they've actually started putting fluorescent orange and green outer coverings on the cables, so the backhoe operator can't say, "Well, I didn't see that fluorescent orange cable in the ground." In the city, they'll actually cut a trench right up the middle of the street with those saws, and then dig out the trench, put in some crushed stone, little standoffs, and then 1 or 2 inch plastic pipes called ducts for some strange reason. Pull the fiber through the duct, and then pour a foot of concrete over it and pave back over it. Now, a foot of concrete, that makes it difficult for somebody to get at those pieces of glass with a shovel. But they still do. I mean, they might have to take the shovel attachment off their backhoe and put the jackhammer attachment on there and go to get through the concrete, and then put the shovel back on so they can cut through the cable. But they still do. Since there is